Good morning, class. I hope everybody is still staying safe and staying healthy and also staying motivated. We will return to the classroom at some point. I don't have a date for you. I'm at home just like y'all. We all quarantining and trying to stay healthy. So once I know something, I'll let y'all know. But in the meantime, in between time, we know we still got a job to do. We got to stay focused because we will be back in class at some point, and this whole program will come to an end at some point, and y'all are gonna be out there ready to start your careers, and can't do that without any of the knowledge. So again, please continue to read your books, stay steady and stay close, stay connected to the industry, watch videos, check the social media of all those guys that are out there that's posting stuff. I should probably post more, but I don't like taking pictures. I'm gonna work on that though. But anyways, um, today we're gonna jump into unit 18. So let me go ahead and share my screen. So chapter 18 is about special refrigeration components. The objectives are identify each special refrigeration system component, explain the purpose of each special refrigeration system component, locate special refrigeration components on a refrigeration system, discuss the need for filter dryers in a refrigeration system. So, introduction. There are a variety of refrigeration components that can be added to a basic refrigeration system to improve the operation of the system, increase system efficiency, enhance serviceability, provide system protection, or ensure safe operation. And so you have a diagram here with all kinds of bells and whistles on it. Zoom in a little bit on that. So there's vibration isolators, mufflers, check valves, receivers, oil separators, accumulators, all kinds of stuff. And we've got all these things we have in class. So we will identify those things when we get back to class, but we have all this stuff. So vibration eliminators, I know some of you've seen this in class before. All it is a braided hose, and it just allows for vibration, almost like shocks. So vibration eliminators. Vibration eliminators are used to absorb some of the vibration created from the compressor. They can be located at either the inlet or the outlet of the compressor, or both. As a compressor operates, it produces some vibrations in the suction line and the discharge line. On larger systems, the vibration could cause abnormal stress on the lines, which could lead to refrigerant leaks on those lines. Vibrations over time can weaken the joint and eventually crack the seal on that joint and spring a leak. So that's something that happens from time to time on larger equipment, which is why on larger systems, often you will see vibration isolators on the suction and discharge lines to just kind of prevent that. Hot gas line mufflers. Mufflers are used on systems to reduce the noise, excuse me, the noise that can be produced by the gas pulsations of the refrigerant being compressed and pumped by the compressor. Mufflers are normally installed on the discharge line of the compressor. Most hermetic reciprocating compressors have discharge mufflers inside their shell. When a muffler is added to a system, it will commonly be placed in the discharge line as close to the compressor as possible. Check valves. Check valves are used on some larger refrigeration systems to ensure that the refrigerant flows in one direction only. They are only located on the discharge line, usually near the compressor. Liquid refrigerant returning to the compressor during the off cycle can seriously harm the compressor on startup. These valves are also used on systems with two evaporators operating at different temperatures and controlled by a single condensing unit. They didn't mention it, but check valves are also used on heat pumps because the refrigerant reverses direction in different modes. So there's usually check valves near the metering device because you have a metering device for your cooling, and you have a metering device for your heating mode. And your refrigerant is supposed to go one way or in one direction through each metering device. So there's a check valve that'll not allow the refrigerant to go through the wrong way through the heating metering device in the cooling mode, or the same for the cooling metering device in the heating mode. So we're used to one metering device, but on heat pumps, there's going to be a metering device at the evap coil inlet and at the condenser coil inlet, because when they switch roles, the condenser becomes your evap coil, so you'll need a metering device at the inlet of the condenser as well. So anyway, there's check valves used to regulate the flow of the refrigerant on heat pumps as well. And the check valve only allows refrigerant to go in one direction and not the other. There's a check valve on your hoses too, on the low loss fittings. When it allows the pressure into the hose, but it doesn't allow the pressure back out of the hose. So as soon as you unscrew your hose, once the pressure is relieved off of that check valve, and it'll seep, back into the closed position. It won't let any refrigerant back the other way. So it works similar to a check valve. Oil separators. Oil separators are used to separate and collect some of the oil in the discharge line as it leaves the compressor and return it to the compressor's crankcase. They are located in the discharge line. Reciprocating and rotary compressors will discharge some oil with the refrigerant as it leaves the compressor. This oil will then travel with the refrigerant throughout the system. If enough oil is trapped in the system, the compressor could become starved for oil, and bearing damage may occur. So the oil separator is just to make sure that the system doesn't rob the compressor of its oil, returning it to the crankcase. Three-way valves. The three-way valve directs the flow of refrigerant to either the condenser or the heat reclaim coil. Three-way valves used for heat reclaim are located in the discharge line between the compressor and the condenser. Some larger refrigeration systems will reclaim the heat from the discharge vapor, leaving a compressor, and use this heat to either assist the heating of the building or assist the building of the domestic hot water for the building. Assist in heating the domestic hot water for the building. Get mixed up sometimes with the smaller words. Need to make it bigger. Oh, there we go. Okay, so heat reclaim coils. A heat exchanger will extract some useful heat for the discharge vapor, and then the cooler discharge vapor will be piped to the system's condenser. Heat reclaim coils used for heating air are located in the the air handling equipment. They are used to provide heat in the winter in supermarkets for reheating the discharge air during dehumidification. Heat reclaim coils improve a building's overall efficiency by using waste heat that would normally be thrown away to heat the building or hot water. So that improves efficiency because you're not only cooling on one end, but you're using the heat that you would throw away on the other end, and you're using that to heat the place. So low ambient controls. Low ambient controls are designed to maintain a minimum liquid pressure during low ambient conditions. Fan cycling and condenser flooding are two methods of low ambient control. Also, adapting or changing the fan speed as well is another way to control that. If the pressure difference across the TEV drops below a minimum value, the value will not feed enough refrigerant into the evaporator and starve it. Starved evaporator is going to equal very high head pressures and will cut your system off. System will not cool. So receivers. A receiver is a vessel that allows a system to store excess refrigerant that it does not currently need. Receivers and accumulators get mixed up often, and one way to identify the differences, for one, the receiver is going to be on the high side, and the accumulator is going to be always on the low side or the suction side. It's good. I refer to sometimes you'll see it referred to as the suction line accumulator. And I like to say it that way because it keeps it in my mind that, okay, the accumulator is the one on the suction line and the receiver is the one on the liquid. It collects the liquid refrigerant, the excess liquid refrigerant that's not being used. So receivers are normally installed in the liquid line of a system after the condenser and before the metering device. Liquid receivers are normally used on systems with modulating metering devices such as TEVs. Receivers are typically designed to hold 20% more than the entire system's refrigerant charge. Relief valves. Relief valves are used to release abnormally high pressure inside a vessel before the pressure causes it to erupt. There are two basic types of relief valves: automatic relief valves and one-time relief valves. Automatic relief valves are spring-loaded valves designed to automatically reset once the pressure inside the vessel reaches a safe level. One-time relief valves, sometimes called fusible plug, is a valve that cannot be reset once it releases the pressure from a vessel. So basically, it'll just break. In other words, it's kind of like a fuse. I guess that's why they call it a fusible plug, because once a fuse breaks, that's it. It breaks as a safety mechanism, but once that happens, it needs to be replaced. Solenoid valves. The direction in which a solenoid valve is installed is important to its proper operation. Normally, there will be an arrow stamped on the body of the valve to indicate the direction of refrigerant flow. A typical solenoid valve consists of two parts: the valve body and its electrical coil. So as you can see right here in this illustration, you got the valve body down here. So all that is inside of there is like a ball valve, and there's a little handle that turns it open, close, and this is your electrical coil. So this is the cord going straight to it. This is your power to energize this coil. You can unplug that and de-energize the coil, unless it's already de-energized if it's not calling. But the point is, once this energizes that coil, then it's going to change position, and then it's going to move this mechanism and open or close that valve. So that's how solenoid valves work. Well, one way to check to see if the valve is working correctly is to disconnect. You can unplug a valve and see if it changes position. Like when it's energized, you can unplug it and see if it changes position. If not, then it's stuck. Liquid line filter dryers. Standard filter dryers have a definite inlet and outlet with arrows indicating the direction of refrigerant flow. Dryers intended for use with heat pump systems are designed to allow flow in either direction. These are called biflow dryers. You definitely 100% always want to make sure, if you're replacing or installing a filter dryer on a heat pump, make sure you double check that. You want to look and see if there's an arrow that has that's pointing in both directions. Make sure you have a biflow filter dryer, or else your refrigeration is your system is only going to work in one mode. It's only going to work in heat or cool. It's not going to work in both. It's going to be a restriction trying to go the other way, because there is a definite inlet and a definite outlet. You can use a biflow filter dryer on a regular AC system, but you can't use a one-directional filter dryer on a heat pump. So biflow, I've in a pinch had only a biflow on my truck and put the biflow on a system that was not a heat pump, and it wasn't a huge deal. It worked fine. There was no problems, but it won't work the other way around. On a heat pump, you definitely have to have a biflow because it goes both directions. In the cooling mode, the refrigerant flows one direction. The heating mode, it flows the other. You're gonna have a restriction once it goes in the other. Also, just another reminder: any and every time you open up a system, you're supposed to change the filter dryer as well. I know we don't do it in class every single time because that would be a whole lot of filter dryers, but in the field, whenever you open a system, meaning when the pipes are cut at any point or any mechanical component removed from the system, like anywhere in the piping, if you're changing the metering device, the filter dryer, or if you're changing out the compressor, or you know, whatever you had to do, you had to repair a leak, anything you do where you have to open the system, you need to put a new filter dryer in, then pull your vacuum, and then proceed with your startup. Okay, sight glasses and moisture indicators. A sight glass can be added to the liquid line to allow a technician to view the condition of the refrigerant in the liquid line at the point it's located, like wherever the actual sight glass is, you can see inside the liquid line. An indicator can also be added to a sight glass to help indicate the moisture content of the refrigerant. So the ones we have in class, it has that little blue dot in the middle, and that blue dot, excuse me, means the refrigerant is dry, meaning there's no water present. And then that same dot can turn pink. I think the color code was blue, pink, and purple. I think purple was like the warning sign, like, you know, a little bit of moisture in the system. And then pink is, okay, you know, you got to pull this refrigerant out. So that dot, in that particular situation, the dot should remain blue. Every single indicator might not have the exact same code, but it should be labeled. So on a properly operating system, the liquid line should contain only liquid refrigerant. A sight glass will show this condition as only clear liquid will be seen flowing through the sight glass. If vapor exists, excuse me, along with the liquid refrigerant, it will be seen flowing through the sight glass along with the liquid refrigerant. The moisture indicator will change color to show the moisture content of the refrigerant. That's something that's mostly used in refrigeration too, by the way. Although you do see them in air conditioning systems as well, but it's like it's like almost like a requirement. It's on every refrigeration system that I've worked on. Strainers are simply filters used to prevent solid particulates or particles from entering metering devices and causing a restriction. They are normally located just ahead of the metering device. So a lot of metering devices have a strainer on it. Like if you were to ever remove a TXV, when you look at the inlet of that TXV, there's usually a little screen right there. And sometimes that's your problem, not the TXV itself. However, it's not wise to take that risk. If you suspect a restriction at your TXV and you pull your refrigerant out, because you can't, it takes almost the same exact amount of effort to check the screen as it does to remove the metering device altogether. So it wouldn't be wise to go through the process of removing your refrigerant and then opening up your system and cleaning the screen and then putting your TXV back together, pulling your vacuum, charging up your system again, test it out just to find out, oh, it wasn't just the screen, it is the TXV. So I say that to say, if you suspect a restriction at the TXV, or if there is a restriction at the TXV, it could be the strainer, but me personally, I don't stop there. I'm just gonna change the whole thing just to be safe and not have to come back. It would save the customer some money if I could clean the screen and put it back rather than charging them for a new TXV. But then I would have to. But then how would you explain to them? Well, it's not that hard to explain to them. Like, hey, you know, we'll try plan A. If plan A don't work, then I'm gonna have to hit you with plan B. I mean, if you want to do that and you explain it correctly to the customer, they'll be down, I guess. But I mean, again, it takes almost the same amount of work. I mean, they got to pay for all that twice. So if I'm going to pull all the refrigerant out and open up the system, I might as well just go with the nuclear solution and just change it out and be done with it. Anyways, evaporator pressure regulators. An evaporator pressure regulator is a refrigerant flow control device that prevents the refrigerant pressure in the evaporator from operating below a minimum value. It is normally installed in the suction line just after the outlet of the evaporator. Evaporator pressure relief valves regulator valves are normally used on systems with multiple evaporators operating at different evaporating pressures. Each of the evaporators operating at a pressure higher than the lowest on the system will have an EPR installed at its outlet. Adjusting an EPR. Turning the adjustment screw clockwise will increase the control point. Turning it counterclockwise will decrease its control point. It may take 30 minutes for the new balance to take place after an adjustment. An immediate response will be seen if an adjustment is made to lower the setting. Adjustment should be made with a minimum load on the evaporator. So whenever you're making an adjustment, you always want to give it some time. Whether you're adjusting the metering device or whether you're adjusting the amount of refrigerant in the system altogether, you always want to, after you make your adjustment, you turn it clockwise or counterclockwise, or you put refrigerant in or you take refrigerant out. Want to give it a while. It says 30 minutes here. I mean, at least give it 10, to see what happens, because sometimes, especially when you're adjusting the charge, when you start putting refrigerant in, your gauges are going to go crazy. As soon as you close the valves, everything you did is going to start to reverse. It's going to start to come back down, and then it's going to bounce around for a little while, and then it's going to stabilize. And if you don't have patience in this trade, because that is one of your most valuable assets, you'll find out, is just being patient, waiting for the system to tell you what's up with it. Because if you're instantaneous, like if you expect instant results every time you do something, you're gonna be chasing your tail. If you make an adjustment and then you record your readings immediately after making that adjustment, 5 minutes later your readings are going to be different, and you're just going to frustrate yourself. So definitely take time in between adjustments and just allow the system to stabilize. Suction line filters. Suction line filters are installed in the suction line before the compressor and are used to protect the compressor from contaminants in the refrigeration system. Suction line filters are often added after a compressor burnout to protect the replacement compressor. Suction line filters are usually removed after the system has been cleaned, or if the filter becomes so loaded with contaminants that there is a significant pressure drop across the filter. So yeah, those are mostly used after a burnout. That's not something you see all the time. Suction line accumulators. The suction line accumulator is located in the suction line just before the compressor. Suction line accumulator stores refrigerant and helps prevent liquid refrigerant from returning to the compressor. So while suction accumulators can be applied to most types of systems, they are often used on systems that cannot use liquid receivers, but have a need to store refrigerant, such as heat pumps. So again, the accumulator is going to be in the suction line. The receiver is going to be in the liquid line. I keep making that comparison because I used to get confused by the two. And so suction line accumulator, just referring to it as such, it just kind of keeps it in perspective. Okay, that is the one in the suction line. The other one, the receiver, is in the liquid line. And the suction line accumulator is there to catch any refrigerant, any liquid refrigerant that may be present before going back to the compressor. Because again, your compressor is a vapor pump, not a liquid pump. Liquid kills compressors. Crankcase pressure regulators. Crankcase pressure regulators prevent the compressor's motor from overloading when the crankcase pressure rises above its design level. The crankcase pressure regulator is installed in the suction line just before the compressor. Crankcase pressure regulators are commonly added to many low temperature refrigeration applications such as walk-in and reach-in freezers. Servicing crankcase pressure regulators. Turn the system off so pressure can stabilize and allow the evaporator to reach a high level. Adjust the crankcase pressure regulator, or CPR, all the way out, usually by turning counterclockwise. Start the system and monitor crankcase pressure and compressor amp draw, turning the screw clockwise until amp draw reaches max allowance by manufacturer. The control set point of the CPR will need to be adjusted on the startup of a new system or anytime the valve is replaced. Always refer to manufacturer's instructions. Suction to liquid heat exchangers. A suction to liquid heat exchanger can be added to improve system efficiency and help prevent liquid from returning to the compressor. The low pressure suction line and the high pressure liquid line are piped next to each other as they travel between the condensing unit outside of the evaporator, outside and the evaporator inside, sorry. Heat is transferred between the cool vapor in the suction line returning to the compressor and the warm liquid refrigerant passing through the tubing on its way to the metering device. This warms the cool suction gas and cools the warm liquid. The effect is to increase both suction and gas superheat and liquid subcooling. This increased subcooling adds system efficiency by preventing flash gas in the liquid line and reducing the amount of flash gas formed in the metering device. So the suction to liquid heat exchanger is just another means of maintaining your superheat and subcool. The whole point of the superheat and subcool is to be sure that there's no liquid going to the compressor, or that there is 100% liquid going to the metering device. And so this would aid in that, making sure that that stays true. Isolation valves. Isolation valves are used to isolate system components when servicing a system. Isolation valves can be stem type or refrigeration service valves. Isolation valves can be stem type refrigeration service valves, diaphragm valves, or ball valves. And that is just so that you can isolate a system. Basically, if you had an isolation valve before and after your compressor, you can close those and change out your compressor without having to pull a vacuum on the entire system, or without having to pull the refrigerant out of the entire system. So in summary, there are many components that could be added to the basic refrigeration system. Some of these components are designed to improve the operation of a system, while others are safety components that protect the major system components and equipment owner. So those are your special refrigeration components. So again, like I say every day, I hope that was helpful. Make sure you read your books. That's going to give you a more in-depth explanation of the same concepts that I just went over. And stay safe, stay inside, do your homework on FlexiQuiz. I'm going to update FlexiQuiz right now, and I'm going to be calling those who need to catch up. So answer your phones. Talk to you later.